Единственное, что как тут менять имя, я не знаю, нужно ли это. Возможно, попробовать. Я сейчас все принесу. Я, честно говоря, не думаю, что надо на твое.
Но подожди, это идет куда надо?
Да, вот оно рекординг, да, оно включилось. Куда надо идет. Видишь, оно само включилось на рекординг. Может, пока выключится рекординг. Так, я несу тебе. Напиши ранее записку, что все в порядке.
אני מחליף את המנהל. לא? תדליק את הפרבוליקה. ואת תאורת צד לאחרונים. טוב, פעם אחת אני מגיע. אבל יש עוד בשלגול, עד דקה לפני החלגול היינו רק הנדרון. לא מגיעים אותה לדקה האחורה, היא קצת סוף.
אני מגיע ישר משיעור אחר, מה שאני נמצא.
מה?
אני מגיע פסקס.
Имя. Получились. Я сказала, что если они Они не виноваты в том, что стирал чуваки. Вакуум присылает, поэтому все просто. Ну, что, на коже, как давать стирать, собрать постель.
Сегодня вы виделся?
А?
Сегодня вы виделся?
Давай заболела. Да?
Ну, треба читати. А ти знав?
Ты можешь проверить, что это? Работает.
Да, рекординг.
Работает. А потом надо будет выключить как?
Потом ты выключишь рекординг, выйдешь нафиг из
А я не
Ну
умею.
что, ты вот делаешь здесь лив.
Лив?
Смотри,
А.
смотри, значит, сейчас так, неважно.
Не
Не выключается, ну, хорошо.
Знаешь, просто лив. Лив я умею. Да.
Да, и принеси мне его в кабинет.
Мгм. Okay. That's it?
It's everything clear, but 4 more minutes.
Yeah, 5.
4
4
minutes.
minutes. Okay.
At least 3 more people.
Immediately not coming back. So it's 2 more people. Okay. Aloni will be late
Okay.
because she has some.
And the third
some
guy is late
morality
always.
lesson.
So, yeah. When you have the ethics and the integrity course.
Exactly. That's it.
She doesn't have an ethics and the integrity course.
So you did something canonical?
No.
You skipped the course?
No, she never did something unethical, so she doesn't need a course.
You don't need a course? Why?
Because you brought up me to be a good person.
But how do they know about this?
I just hope that they won't check.
Okay. So maybe they won't know that you're skipping, right?
All about interpretation, plagiarism, and
About it.
falsification of.
Okay, so as you understood, Rami is ill today, so I will be replacing him. Oh, we are still waiting for somebody.
Have 2 more minutes.
קורס של יורו. תגיש לי את המטרה, אני אעיף אותך בשאלות ואת תטעיתי ב3, קיבלתי עובר, זה לא בסדר.
Okay. So the title of today's talk is Multiplicative Structures on Categories. So I will explain what are monoidal categories, symmetric monoidal category. Oh, I will try to explain and give some examples. So let us start with something we know better. Monoidal structure on a set. It's an operation, binary operation, that is associative. Unit element that satisfies standard properties. And this is, of course, shortcut instead of writing n of 1a. Okay, understand this. So associative, well, the axiom of unity, that's it. This is a monoid, okay? Almost a group, but no inverse. Well, what is a commutative monoid? Well, of course, we know the same, but with an extra property. So we want to discuss similar structures on categories instead of sets. So this will be a special case. We know that any set can be considered as a category where there are no interesting morphisms instead of identities. But of course, this will be a very trivial case. To start with something, before this, sorry, I want to explain, well, widely well known, but still to stress some meaning of associative property. Okay, why are we interested with this property, which is A times B times C equals A, B times C? Associativity allows one to make sense of multiple product without putting brackets. So however we decide to calculate the product using the binary product, we will get the same answer when we don't change the order of the factors. And commutativity means the same, but also we are allowed to change the order. Okay, so it means that the collection of arguments is not a sequence, but just a finite set. Okay, very well. So this is all we want to know about multiplicative structures on sets. Now we pass to categories, and we want, of course, some natural examples to be examples of this. And so let us look at the simplest example and see what has to be changed to make sense. So very approximately, we can say that a monoidal category is a monoid in and a symmetric monoidal category I will write Sn. Is a commutative monoid. So it's very important to understand why the very naive definition of this is not very good. So let us take an example of something that we know or feel that has to be a symmetric monoidal, a monoidal category, or even a symmetric monoidal category. Have you something in mind? Well, sets with operation
Cartesian product.
Cartesian product. Very well. I will, in general, I will denote the operation like this, but in our case, it's just Cartesian product. Okay. It's associative and commutative, and it has a unit which is one element set, right? Very well, but x times y times z is not, or not exactly x times y times z. Well, it depends on how you define Cartesian product. Let us assume that we define Cartesian product as a naive set theory, as a set of pairs. Okay, then objects, so elements here are pairs. An element here, which is also a pair, and an element in C, right? These are typical elements here. And here typical elements are pairs X and the pair YZ. You can say that this is the same, but this is not the same. If you think about what is a pair, so the first element of this pair is XY, and here the first element is X. So they are not the same. But of course, we feel that they are more or less the same. And what is a correct formal definition? Of course, there is a natural isomorphism between these two. Okay, very well. So instead of equality, you have a natural isomorphism. This is first change in here. So what is the map from A times A to A? Well, probably this is a functor from C times C to C, which is bifunctor. Well, yes, in this naive definition of direct product, this is a bifunctor, even though in general categories, I believe you studied what is a Cartesian product, what is a direct product. It's not something well defined. It's something defined by universal properties. So it's unique up to a unique isomorphism. You should work not very hard, but you need a work to make from this assignment a functor. I don't know whether you discussed this or not. The assignment to any two objects. Let us take a category that has products. Okay? It means for any two objects, you have a product. It's not unique. So you have to think a little bit to choose a functor from the direct product of two categories to read that to any pair of objects assigns their product, because it's not unique. You should choose it, and then to explain that this gives you a functor. So even here you have some problems. Okay, let us call it A, because this is, well, alpha, because alpha is associativity isomorphism. Okay. Well, unit object. What is unit object? One element set. You have a lot of one element sets, so you have to choose one. It's easy, but still, it's not so obvious that that somehow if you choose another one element set, you will get to some extent equivalent monoidal category. So I'm showing that there is a lot of different questions that appear. Each of them doesn't seem to me to be very serious, but somehow if you want to be on a solid ground, you have some problems of language. So, okay, so you have this map. You have an object. Okay, I will choose my favorite one element set. I will denote it like this, and I will get this object. Now, 1 times x, well, it's not x. It's something that is isomorphic to it. So you have to choose isomorphism. You can do it, of course. So this is also part of the structure, right? I multiply from left, so I call it lambda isomorphism. And of course, x times 1 is another thing. This will be right. And of course, these are all data of isomorphisms. And what is the most terrible thing is that there are certain compatibilities. And this is a very, very long list. Okay, let me write down the most interesting, the most interesting compatibilities that have a name. Okay, so these are compatibilities of alpha with itself. This has a name. I will call it Stashev improvement. Pentagon is the shape of the diagram. I will show it here. And Stashev is the name of a person who is, to the best of my knowledge, still alive. He invented this in 1963, I think. But he was young then. Okay, so how do we get these compatibilities? Imagine that you have 4 objects, not 3, 4 objects. X, Y, Z, T. So now, I don't know, you already understand that I'm starting to present a definition or parts of definition of monoidal category in general. So it's a category with a bifunctor like this, with a map, well, alpha canonical isomorphism from x times y times z to x times y times z. What do I mean by this? This is a notation for a certain functor from c to the power of 3 to c. Right? To each 3 objects, x, y, z, you assign an object here by this formula. And this is a functor. This assignment is functorial because from the very beginning, we have a functor from this. and don't be too critical that I don't want to think that what does c to the power of 3 mean? How do I compose? Oh, okay. No. That's actually said here. So, this is a collection of triples without specifying triples, pairs, of pairs in one way or in another way. Okay. Everybody understands what is a triple. Now, the fact that this is a canonical isomorphism just means that this is an isomorphism of two functors. We have left-hand side give a functor from c to the power of 3 to c. The right-hand side gives another functor, and you have a canonical, you have an isomorphism of these functors. This is what we mean when we say canonical isomorphism. Is that this is isomorphism of certain functors, usually clear what functors. So now we have 4 objects. We can do the following, and using this alpha, we have an isomorphism. I write an arrow, but it's not very important because it's isomorphism. It's x times y times z times t. How did I get it? I applied to the first bracket alpha, and just I retained t, because then this tensor product is functorial. So if I have a functor here, I can multiply it by t. Okay. What can I do further? I can apply alpha to these 3 guys. So there was product of x and yz, and then by t. So I can multiply otherwise, and this will get x times y times z times t, right? I can go in the opposite direction and say that just a moment. It's better just to see what's going on. So now we have,
Like you can say one set of brackets around x times y and another around z times t. No.
yes. Oh, yeah. So I retain this, and here I change this bracket to this bracket. So it will be x times y times z times t, whatever. So what can I do now? I have x times y times all this guy. So I retain this guy, and I say x times y times z times t. Okay? And now we have this. X times, maybe it's worthwhile to write down. Here alpha is Y, Z, T. Here, alpha is X, Y, Z, T. Here, alpha is X, Y, Z. And here is alpha X, Y, Z. And this is alpha X, Y, Z. Okay? The requirements for this diagram is complete. Well, I don't know how to persuade you that in real life this happens. Maybe we will discuss later. But maybe even the more interesting question is, how do we know that this is all we need to require? Okay? Maybe there are more sophisticated data. Okay? That has to be, of course there are. Like, similarly to what I said on multiplicative structures on monoids. We actually, associative structure on, associative structure on a set. We actually want to say that the result of product won't be dependent on the way we multiply. We put brackets, okay? For any product of n elements, we have some diagrams, yeah? We have some possibilities, and they are all the same. Here, we want to say something similar, but we don't say that they are all the same. We want to say that they are isomorphic, well, with a specified isomorphism, and there is a unique isomorphism connecting each 2 points. This is why this diagram has to be required to be commutative, because any 2 ways of calculating things lead, well, not to the same object. Some clever people say that in category theory, you are not allowed. Your formula can say that 2 objects are the same, but you should think that this is not allowed. Because category will not change if you add 1 more object, which is isomorphic to another object. Yeah, we want to use the language which doesn't feel difference between equivalent categories. So we cannot say that 2 objects are the same, but we want to say that a certain amount of objects are all canonically isomorphic. What it means canonical isomorphism? There is a canonical isomorphism between any 2 of these objects. And this already can be said. And this is the simplest diagram we get. It's called Stashev pentagon. And there are, of course, more sophisticated diagrams that include more objects, like here. But of course, they are not called pentagons. They are called I think, well, this is more or less accepted term nowadays. So let's see. Associator. So these are polyhedra that describe associativity. And you can describe them. These are convex polyhedra such that pentagons are their faces. Whether all faces are pentagons? No, maybe there are some sort of degenerate faces which are squares. I don't remember precisely. But that's the picture, that's the name. You can Google it or whatever. So Stashev, Jim Stashev is the name. Okay. So that's more or less definition of monoidal category. It's not a full definition, but once you understand it, you feel pretty safe working with the notion. Whether I'm able to give it a full definition, well, I will say what is missing here. Unit is missing here. Unit is, of course, well, an object together with isomorphism of functors, identity, and multiplication by this unit on the left and on the right. And of course, there are some requirements which do I know how to write them down? Maybe I wrote them. So actually, I don't like, of course, these definitions. I think nobody likes them. I will describe you how to find a better language, well, to some extent better, a much simpler language to talk about monoidal structures, in particular about monoidal categories, but just a moment. I think I have somewhere. Yes. Here is the axiom required for the unit. Once more, the axiom is obvious, but somehow we don't know whether it's all we need to require or maybe some other trivial thing should be required. No, the answer is no, it's enough. And here is the diagram. X times 1 times y. You have this left multiplication goes to x times y. You have this associativity constraint. Yeah, this is an extra word. Constraint. I don't know how to translate the word, but instead of associativity isomorphism, people usually say associativity constraint. So alpha goes to x times 1 times y. And here you have lambda, not lambda, rho, x times y. And here you have identity. Yeah. No doubt we need to have this axiom. The question is whether it's enough. It is enough. So we can say approximately or very precisely the general recipe. If you have two objects that are connected in two different ways by composition of these constraints of unit constraint, lambda law, and of associativity constraint, then this diagram has to be commutative. So there should be a unique identification of them. So the idea is that once you categorify, once you pass from a set with multiplicative structure to a category with multiplicative structure, instead of saying that some object is unique, or like product of n elements is unique, you are saying that it's unique up to a unique isomorphism. You can get them in different ways, but then there is a unique isomorphism between them. Practically, it turns out this is a sort of topological theorem. I will explain what I mean. Topological theorem saying that in order to make sure that there is a unique isomorphism between any two expressions, you only have to verify Stashev pentagon and this diagram that has no name. Okay? Why I'm saying that this is a topological claim? Approximately because you describe all possible ways of moving from of composing these maps, and you get edges of some certain convex polyhedron, and you describe its faces, which are just like this and nothing more than that, and that's approximately the proof. This can be found somewhere in a very important book by McLean. It's called Categories for the Working Mathematician. Well, you can find it. I don't know whether you have to read it or something, but that's a reference. He was interested in these questions. It's called, all these questions are called covariance theorems. Means that different compositions are compatible. Well, the diagrams commute. For instance, one of these theorems says, well, I will say something that obviously has to have sense. I don't know whether we're ready to discuss it. That if you have a monoidal category, you can replace it with an equivalent category, equivalent monoidal category for which unit is a strict unit, meaning that 1 times any x is equal to x. And associativity is strict associativity. Well, from contemporary point of view, usually people would say that, well, that it's a meaningless, useless claim, because in category you are not allowed to say that two objects are the same. But back in 60s, it was an achievement, saying that even though there are some problems to define what is a monoidal category, this does not, imagining that everything, all operations are strict, do not lead to any real problems. But so once you're careful enough, you will get correct result. By the way, it won't be so for symmetric monoid. There are also theorems about covalence there, but I'm not sure I know how to formulate. Even this theorem, we don't know how to formulate because we never discussed what is a monoidal functor. You can imagine it's also not so easy. We know what is a functor, but, well, how should it be compatible with tensor product? Definitely, you do not expect it to be compatible on the nose because there is no such. So there should be a canonical isomorphism between f of x times f of y and f of x times y. And then, of course, once you came out with this notion that there is a canonical isomorphism, you should understand that there are probably some compatibilities. And I'm not sure I want to discuss this, but about the formulation of the strictification of monoidal categories, the situation is easier. You can imagine that once you have a monoidal category and a functor from it to an equivalent category, this should allow you precisely to move monoidal structure to the other side and to get an equivalent monoidal category. That's somehow what you expect, and this is true. Okay, what are interesting examples of monoidal categories? that are not symmetric, even though we haven't discussed symmetry. Okay, the first thing that comes to my mind is the following. We have a associative link. And you have the category of bimodules over this ring. Have you heard this notion? It's not very difficult. I will tell in a moment.
Right and left.
Both right and left. I don't know actually how to write. I will write like this. Modules, left and right. So you have left multiplication by elements of R, you have right multiplication by elements of R, and somehow they commute. Oh, which sounds obvious, yes. M A B equals A M B. Actually, this is associativity condition, but you can say that it means that left multiplication and right multiplication commute. So yeah, which tells us that commutativity and associativity are two sides of more or less the same thing, which has maybe more than two sides. Okay. Actually, this was my invention when I was a first-year student, because I thought I want to invent some new algebra. So I will not only multiply horizontally, but also vertically. It turns out that if you allow yourself to multiply both horizontally and vertically, and well, each operation is associative monoid, then these two multiplicative structures coincide and are commutative. Have you heard about this?
Yes.
You could have heard about this in algebraic topology from
We heard it from Rabbi.
Rami. Ah, very well. Yeah. Okay. But yeah. It's called Ekman-Hilton argument. Describing why higher homotopy groups are commutative. Okay, so this is a monoid, a category of bimodules. Multiplicative operation. Given two bimodules, I will write like this. I'll assign to them m times r n. Here I use right R module structure on M and left R module structure on N. This will be also a bimodule because it will retain left module structure from that on M, and it will retain right module structure with respect to from N. So this is a bifunctor on bimodules, and it's associative in our sense. Well, tensor product of three guys. Of course, it's important how we put brackets, but up to isomorphism, this is the same. And it's not commutative at all. So this is a typical monoidal category which is not symmetric. Well, another typical example, well, maybe it's enough, okay? Well, I will just say this in words, if somebody is interested. There are Hopf algebras. And you can, and represent modules of a Hopf algebras are have a bimodal structure with respect to tensor product over the field. Okay, let me say this in a few words. H, Hopf algebra. Hopf algebra means that a part of multiplication we have a co-multiplication. And there, of course, there is a compatibility saying that this is a homomorphism of algebras. Then, if you have two modules, over H and tensor N, tensor over K, over the field, is a module over H times H. And then you can use this co-multiplication to get an H module structure. So there are some interesting monoidal categories that are not symmetric.
Could you give an example of a Hopf algebra?
Yes. For instance, if you have a group G, then group ring is a Hopf algebra that delta of G is G times G. And modules of a group ring are representations of group. And tensor product is tensor product of representations. Okay. So you could have been curious. Tensor product of modules over the base field usually do not exist. But for representations, for modules over the group ring, it does exist. Why? Because this is a Hopf algebra. Well, the same story, if you heard about Lie algebras, is the enveloping algebra over a Lie algebra. This is also a Hopf algebra, and it's defined, well, it's less clear why does this define anything, on elements on the Lie algebra by saying that delta of x is x times 1 plus 1 times x. Then modules over the enveloping algebra are just representations of Lie algebra. And tensor product is tensor product of representations of Lie algebra. So this is a meaningful notion, but in these cases, this is this monoidal category, the structure is symmetric. Why? Because this co-multiplication is sort of commuted in these two examples. But if it is not, it won't. Okay, What did I intend to say after this? Okay, now we come to symmetric monoidal structure. So the question is, what should be added or changed in order to talk about commutative monoids in the realm of the well, we have to categorify the equality. What can we do? It turns out that there is no unique way to do this. There are at least two ways to do this, but we will discuss it later. Of course, instead of equality, we will have a canonical isomorphism. So, okay, title is symmetric monoidal categories. And of course, you should add canonical isomorphism from x times y to y times x. Which means, I repeat, isomorphism of two functors. One is multiplication and the other one is just swap and multiplication. Okay? You know, formal way of writing this down is M equals M composition with, well, let it be sigma, and this is S, when S of xy is yx. Okay, this is just swap of two elements, and this is equivalent to this. So here we have a canonical isomorphism between these two functors instead. Yeah. And of course, the question is, what are the extra compatibilities? That has to be required. Now I will use the moral meaning of associativity constraint that says that any two ways of writing down tensor product of different objects are canonically isomorphic. So I will not specify them. I will write as if they were equal, but meaning that they are canonically isomorphic. Okay? Otherwise, the formula becomes worse, and you can see once more in MacLean's book, a more careful writing down affairs. He has, by the way, he has separate definition. Strict monoidal category means that this is just monoid in categories. And non-strict monoidal category, this is the one that actually exists. Okay? What are extra compatibilities? So first of all, there are some compatibilities with the unit, which I can hardly imagine what it is. But let me show you important ones. The first one is the following. Let us assume that you want to you have three guys. And of course, you can replace this two. You will get z times x times y. As I said, I will change the brackets according to my needs using associativity constraints. So for me, this is the same as, it's not equal, but I will pretend it to be equal to have a little bit simpler diagrams. So it's x times y times z. But what I really want to do, I want to interchange z and y. And then I will get x times zy. Okay? So this is sigma and this is sigma. And this is already nothing. We understand everything about this. Okay. Now here, I want once more to replace brackets as I wish. With the only aim to replace this. Well, I can already. And this are the same. Okay, so you can think of this as hexagon, but I prefer to think of this as a triangle. Because these edges are, we already have got accustomed to them. Okay, so this is one condition. I think there should be another one, a symmetric one. Yes, there is a symmetric one. And of course, this is not everything, but it turns out that if we retain only these axioms, plus the axioms about unit, which I don't want to write them. I don't remember them. I have to find somewhere, and well, you can imagine what it is. Okay. But it turns out that these axioms give an interesting notion, and it's called braided monoidal category. So actually what it says that you're allowed to transpose two factors, and if one of them is a product, you can do it in, one after another, right? Why is it not necessarily symmetric? Let me say, what is axiom for symmetric? You have your sigma. Let us denote it sigma with two indices, x and y. And you can apply another sigma with two indices y and x. Now, do we want this to be identity? So do you expect sigma to be an involution? If you do, this is a symmetric monoidal category.
I want it to be equal. Is equality?
No, equal, but not the objects. But you have this composition and you have identity map.
Yes.
You want these two maps to be equal. You're in conventional categories. You don't have higher categories. So you can compare two errors and say whether they are equal. The set of maps is a set, not a topological space or whatever, or category or whatever. So you can compare them. So if this is the same, it means that once you make twist twice, you get what you had. Then this is a symmetric monoidal category. If you do not require this, this is a braided monoidal category. It's a weak condition. Unfortunately, I don't have very obvious examples of braided monoidal categories that is not symmetric. So actually, when I prepared this lecture, I thought that I wouldn't mention braided. But somehow, once you just list the axioms, it appears very naturally that once you have said only part of them, you're already done. It's a break. To show you the difference, let us take okay, so we have 2.5, or we have three notions: monoidal category, braided monoidal category, and symmetric monoidal category. Let us think what can be said about, well, let us choose one object and take its tensor power. Nth tensor power. Since it's monoidal category, this makes sense. Well, I allow myself a little bit more than, okay. To calculate this, we have to put brackets in and make calculation. And depending on the brackets, you will get different answers. But they are canonically isomorphic. So there is a unique isomorphism between any two. Unique in the sense that we can point out a unique isomorphism between them. So as an object, it's more or less defined. Well, we often say that this is the object, meaning that it's object defined up to unique isomorphism, right? In category theory. For instance, product of two objects in a category that has products is unique up to unique isomorphism. We allow ourselves sometimes to say that this is the product. Okay, so you have this object. What does braided or symmetric monoidal structure give? Yeah, I want just to show the difference between braided and symmetric monoidal on this example. Well, you have this isomorphism that allows you to interchange different properties, right? You can compose them. What will you get? I claim that if C is symmetric monoidal, then you have the action of symmetric group on this guy. Why? Well, because symmetric group is generated by simple, how you call it, transpositions. Sigma I that are I plus 1. And this is precisely the automorphism from x times x. You have here I plus 1, and you transpose them. Okay, you understand? Well, you have to verify that this gives you the action of symmetric group. Maybe you know that symmetric group is not only generated by these guys, but you have explicit set of relations with them. The relations are each si squared equals 1, right? If you transpose twice, you get nothing. This is precisely the symmetricity condition. Another condition is that Sj equals Sj Si if they are far away from each other. And the last condition, when when this is I and I plus 1, then you get Si plus 1 Si equals Si plus 1 Si plus 1. That's it. Well, that fact has nothing to do with category theory, but it's a nice piece of knowledge. So this should be precisely, or more or less, equivalent to this condition, which means that if you have a braided monoidal category, if you have a monoidal category, you have a notion of x to the power of n. Meaningful notion, meaning it defines uniquely up to a unique isomorphism. If you have a braided monoidal category, well, if you have a symmetric monoidal category, you have the action of symmetric group on this. Now, some people know that there is another group which is also very interesting, which is also generated by these elements, which also has this relation and this relation, but not this relation. It's called the braid group. Have you heard about this?
Oh, I think you need second relation, and you will go through.
Yes, sorry. It's called braid group. It's a geometric object. Symmetric, you have two lines. You have n nails here and n nails here. And, well, permutation is given just by one-to-one correspondence between n nails here and n nails here. And you know how to compose them. Now, if these are really nails and these lines are chords, okay, then once they intersect, they do not really intersect, but one is above and the other one is below. So if you have identity permutation, but no, I'm confused. This is a simple reflection, and you compose it with itself once more, you won't get identity member. And it's a topological fact. Once more. So this means that S squared is not equal to is not equal to 1 in the braid group, only in the symmetric group. So that's what is happening with braided monoidal category and symmetric monoidal category. Okay. Now what I want to do, we have a lot of time before the so
We have a break.
okay, let it be a break.
10 minutes.
Huh?
10 minutes.
10 minutes. Okay. Good.
Можешь, пожалуйста, объяснить? Вот у нас вот есть вот эти отображения альфа, x, y, z. Вот как они устроены? У нас альфа, x, y, z, у нас
Значит, как вот это? Вы просто забываете об этом. У вас есть отображение из первого выражения во второе. Согласны?
Да.
Ну, а теперь, если у вас есть отображение, есть стрелка в категории, тензорное произведение на t – это функтор. То есть он стрелку эту.
Что, хорошо. У нас здесь сейчас, здесь это все изоморфировано, но только они со стрелками непонятно работают, да?
Но нет, они изоморфизмы, да. Это изоморфизмы функций. Тебя это только English было.
Sorry.
Вы вчера спрашивали, почему знаки возникают в супернауке. Я вам сейчас
семья.
Что?
Такая маленькая семья.
Я вам сейчас скажу.
На лекции.
Ну вот, да.
Хорошо.
When you're talking about isomorphisms of functors, so you mean natural isomorphism? Right?
Yes, yes.
So now we see that we have a functor from our category to category of functors from braided groups to our category, right?
I don't understand. Once more.
So here you showed us that
I showed that given an object
in an object we can
in a braided category, you
Yeah.
have a representation of well,
we can
not really a representation,
Yeah.
depending on.
but actually we have a function from EM to to category C, which assigns to the our only object x to the power of n and every
You wanted to say BBN. Yeah.
yeah.
BBN.
Yeah. I don't like
Yes.
recitation. Yeah. For every m.
Well, it's
But
this notation makes a lot of sense. Of course, if you have B in two different senses, it's confusing. But why it's BG? Well, what notion of BG do you know? In topology?
yeah, I heard about classifying space.
Okay,
This is-
okay. Geometric realization of BG is the classifying space.
Yeah, that's different. Okay, that's not the
Okay,
question.
okay. Sometimes it's confusing, yeah, because it's a very close notion. They are connected, but not equal as in categories.
So here we have a function from C, I think, to the functions from the n to C
Yes, yes.
for every n.
Whatever.
And is it equivalent to have a monoidal structure or braided monoidal structure or not?
No, of course not. Because first of all,
And how far is it to be?
well,
From
I think it is so if your category, well, but I haven't thought about this. But first of all, your construction knows nothing about arrows in your category that are not isomorphisms. So you can discard all non-isomorphisms. You will get a groupoid, which is also a monoidal, a braided monoidal category. And for braided monoidal groupoids, maybe you're right. But I mean, I don't know. Maybe.
But do we have any methodic results which we can get from such theory? I mean, like, if we explore some methods, we can get.
So, I saw the definitions and maybe not understood what.
Oh, the question is these science related to some combinatoric problems. Is it possible to get something something non-trivial, but what we can formulate using only combinatoric.
I don't know what to do. So, to the best of my understanding, the only thing which is close is this braid group actions and things like this. So this is not precisely okay. But you probably don't precisely know what you're going to do.
I don't know. I just.
No. If I knew what to answer, I would. So how much time do we have?
About 23 more minutes.
No, I mean, I thought.
21 until 1.
Okay, yeah. Okay.
The usual definitions of the monodal categories of symmetric are just given the natural isomorphism. So we are actually talking, we are actually.
I intend to give a very nice approach that allows one not to care about all these constraints. The only problem when I prepare the class, the only problem I see, but it's a serious problem, is that in this definition, if you have a monoidal structure on a category, it gives you automatically a monoidal structure on its opposite. And my very beautiful approach that avoids everything cannot do this. But you'll see. Okay. Should we continue? Well, now I want to explain a major difference between monoidal categories and symmetric categories. I won't talk about braided categories. I have nothing to add. A part of the fact that they used at least to be very popular in physics and knot theory and things like this. It's connected to quantum groups. Okay. But something much more basic. As I said, there is maybe useless theorem by MacLean saying that any monoidal category is equivalent to a strict monoidal category, where all, which is just the monoid in the world of categories. Now I want to explain that this is impossible in the world of symmetric monoid. So you can strictify associative structure, but you will still have the braiding, the isomorphism between x times y and y times x, and you cannot do it just equality. This is what I will show you in examples. So, okay, so I want to consider the category of graded vector spaces. What is graded? Z2 graded vector spaces. I will say G graded, but G will be Z2. Okay, so what it is? The object is V0 plus V1, or you can just say a pair of two vector spaces. Okay, zeroth component and first component. When 0 and 1 are elements of C. Meanwhile, as a category, it's not important. It's just a product of two categories of vector spaces. Morphism. Home from V0 plus V1 to W0 plus W1. Of course, these are maps that carry V0 to W0 and V1 to W1. It's just home of vector spaces V0 to W0. Okay, that's clear. So I described you the category as a category, right? As a category is just product of two copies of vector of category of vector spaces. Okay. Now I want to describe you as a monoidal category. So what is tensor product of V0 plus V1 and W0 plus W1? Okay, you have zero components and first component. The idea is that once you multiply elements of different gradings, so it gets grading corresponding to the sum of two gradings. Well, our operation is plus. So it's V0 times W0, but also V1 times W1, because 1 plus 1 is 0. And here V0 times V1, V0 times W1 plus V1 times W7. Okay, that's clear. I'm not talking about associativity constraints. They are usual associativity constraints in which we usually ignore them. But now I want to have a symmetric monoid. And I have two non-equivalent examples. So we can define braiding and category of Z2 graded vector space in two different ways. First, we can just think of this as two copies of vector spaces. So it means that you have usual braiding. It means S of V0, V1. No. S of V W equals WV for all homogeneous elements. Actually, this will work for all elements. Okay. Just usual transposition as in vector spaces. The second braiding is called super. Means S of VW is usually it's WV, but sometimes it's minus W. Well, yes, there is a unique form. Minus 1 to the power of A times B, WV. When B is in VA and W is in WB. So the only case when you have minus sign is when V is in V1 and W is in W1. If both are odd, it's called odd part. Even part of this odd. Once you transpose to odd elements, you change sign. This works and this works. These are essentially different symmetric monoidal structures on the category of Z2 graded vector spaces. Whether this is important? Of course, it's important because it's just slight generalization of the category of vector spaces. Instead of one vector space, you have two. It's not a big deal, but this may happen. But this is also important thing. Okay, I will add something that, of course, I had to tell before. Let me tell it now. One of the aims, one of the reasons of existence of monoidal categories is that in a monoidal category, you can define the notion of algebra. Let C be monoidal. Define an associative algebra in C is an object, a multiplication, well, you have to have the bifunctor to use, so you need at least part of monoidal structure. And, well, you want also to have unit. What is unit? It's not an element of A, you don't have elements, but you have a map from unit object of the category of A. Pay attention, if C is category of sets, unit object is a or the one element set. Then the map is just an element of A, which is okay, which is what we want. Okay. Okay, unit. And well, I won't write down axioms of unit. This is less interesting. Interesting is that to write down axioms of associativity, you need associativity constraint. Because you don't have A times A times A. But you may write it down like this, or you might write it down like this. And you have associativity constraint that allows you to compare them. And then you have a map. Identity A times M, which is A, right? And then you have a small m, you get A. And then you have n times identity A, which is A times A. And then you have n, and we can say that this diagram is complete. So this is associativity. You wouldn't be able to write it down without associativity constraints. So monoidal categories allow you to define associative algebras. Okay. Similarly, if you want to define commutative algebra, you need symmetric monoidal. Well, you have everything as above. But you also want this is C. And you want to say that this is commutative. Well, you could have asked, do we really need symmetric monoidal category? Maybe it's enough to have a braided category. I think that I saw things like this. I don't believe it. Well, formally it's correct. You can do it. But somehow it. So it means that sigma is not an isomorphism in general, but probably it is once you apply it to the fixed element. So I don't feel that I like this notion. That I believe that this notion makes sense. Okay, but I think I saw papers when people discuss this. Okay, so to talk about commutative algebra, you need symmetric monoidal structure. And now I want to continue my example of superspaces to show you that these superspaces really appear in nature. We know about this. So let us take a smooth particle. You don't like smooth manifolds, you can take just Rn. It's a smooth manifold. And there is something called Dirac complex. So these are just smooth functions on X. These are one forms, differential forms of degree one. For Rn is just smooth functions. Well, free module generated by dxi. A form looks like some fi dxi, at least local. Okay, these are two forms, etc. So you have dxi, dxj. Okay, and we have a differential. The differential is more or less uniquely given, plus some maximums uniquely given by the property the differential of f is what you know it should be. So df dxi dxi. That's the proof. And differential squared equals 0. So differential of f dxi is some df dxi. Well, this doesn't follow, but still it's true. dxj dxj dxi. Okay, something like that. Heard about this? Well, it's worse. Okay, you are doing computer science or something like that?
No,
No,
I don't. I do some number theory.
number theory. Well,
But
okay,
I
then you have to
I
know
went
this.
to know such stuff.
Then you have to know this, yeah. Okay, so you have this complex. And we know that this is a commutative algebra. It means that if you have omega in omega k, omega prime in omega L, then you have a product, and omega prime is -1 to the power of k times A, omega prime of, okay? For instance, one forms dxi dxj equals minus dxj dxi. This is degree 1. 1 is odd number. So you see, it's a commutative algebra with respect to symmetric monoidal structure on what? On the category of complexes. Complex, everybody knows what is a complex? Complex is a sequence of a billion groups or whatever you want with maps between them such that d squared equals 0. That's a complex, okay? So what is the symmetric monoidal structure on complexes? Well, complex is first of all a graded object. It's not Z2 graded object, it's Z graded. But there is a strange result that says that actually the only non-trivial braiding appears from Z2. So if you have a Z grading, then somehow it factors through Z2. As you see in these formulas, everything depends only on K and L being odd or even. So at the end, you have Z2 grade. And you cannot define, so this is a graded object plus certain differential. So in order to define symmetric monoidal or even monoidal structure on complexes, you should say how to, given two complexes, M and N, how to define M times N as a complex. So complex has two components. It's a graded thing and a differential. So you can do it separately. So this is tensor product of two graded objects. You define it, well, in an only meaningful way. Nth component of this, I prefer to write down upstairs because here we have upper indices. M times N. Nth component is sum NP times NQ, P plus Q equals N. You add the degrees as usual, okay? The differential you define, well, according to the Leibniz rule. Differential of x times y is dx times y plus, well, that's the only option, -1 to the power of degree of y x times dy. You cannot avoid doing this because otherwise d squared won't be 0.
I think here should be a degree of x because
Yes, of x, of course. You're right. So if you don't do this, you won't get d squared equals 0, and this is not what you want. Now, if you want to marriage this to braiding, you cannot put the trivial braiding. You should put the braiding which takes care of the science. So that's the only way you can live with you can make algebra. You can make an algebra of differential forms, and basically in homological algebra everywhere, since homological algebra works with complexes, and we like to have monoidal structure, this sign rule, which when I was a student was called Kozuri sign rule. The notion of symmetric monoidal categories already existed, but somehow very few people outside of category theory community knew it. So it was Kozuri sign rule that for some reason you have to add these signs once you interchange two entities that have degrees. So this is the only possibility to be in the world of symmetric monoidal categories. Okay. So that's it. I have 1 more hour, and I want to devote it to presentation of a way to define all these objects without any associativity, commutativity constraints, ratings, and all this. So everything will be very easy, set theoretically. And also, what is good, you won't have to think about how to define a functor between such things. Here it would be also a pain. People didn't, but they were much cleverer than we are. So well, okay. So now I present a sort of more contemporary approach that allows to simplify the explanation. But it has one serious drawback, which I don't see how can be overcome. As I already said, I think. In this new approach, it's very easy to define these objects without all this machinery of commutative diagrams. But I don't see how to say that if you have a monoidal category, its opposite is also monoidal category. You will see. Okay. So now I will define some sort of set theoretical object, which will replace all these notions of monoidal categories, which has a nice name, opera. And approximately equivalent names, multi-category. Okay, there are some variations, some of them we will discuss. So I will start with the notion that corresponds to monoidal category, and this is planar opera. I will denote it C because it will be very close to categories. Planar opera. So it has a set of objects. We are not doing set theory, so class set for me it's the same. And then you remember what is a category? It's a set of or class of objects, and for any pair of objects, you have a collection of a set of morphisms with this source and this target. Here, the same, but you're allowed to have a sequence, a number of sources and one target. So this is why it's multi-category. Okay. For any sequence x1, xn, finite sequence, and also another object y, we assign a set I will write it like this. So our notion of morphism is a little bit generalized. It has a number of inputs and one, okay? That's a nice picture. Well, category also has compositions. What are compositions here? You can imagine. You draw some guys here. You have, at the end, I have Z, Y1, Y3. And for each, I have X1, 1, X, M, 1, 1, X, 3, no, 3, 1, X, 3, M3. You just get a map from all this list of inputs. Okay. Very nice picture. Very nice generalization of a category. What is missing here? Identity maps. Identity maps is a map from okay. It's one input, one. Okay. Axioms of associativity. It's strict associativity as an usual category. You don't have to think about them. Right? Axioms of unity, it's strict unity as in set theory, not as a category. Okay, that's planar operator. Why planar, you may ask?
So to be clear, that's you think either category which objects is all subsets of objects in the previous category and morphisms are not.
No. It's not a category.
We don't-
It's a sort of generalization of category. Any category can be made like this if you say that the only morphisms we have one source and one
I
target.
see.
But you have multi-linear maps like
So we don't have morphism without with two sets between two sets. So that's not a category, I see.
that's not a category because category has morphism only from an object to
Right.
you can incorporate this into a big category whose objects are sequences, but then you have to define what is the map from one sequence to another, and you can do it, and people do it, but I don't want to spend too much on this. That's an interesting combinatorial notion that was invented in mathematics, in algebra, many times. And people didn't know each time that they invented something exists. So, for instance, Beilinson once invented this thing and called it pseudo-tensor category. Much later than the notion of opera. The notion of opera also appeared in algebraic topology in the 60s. Okay, that's operator. Okay, clear what it is, right? What is planar in this operator? I can tell you. If you write down these pictures, you can put them on the plane. Okay? because here the set of sources is ordered. So you have to, once you glue, take a composition of morphisms, you have to take the order of all this. And of course, you use lexicographic ordering, but it precisely means that your tree will be a planar tree. Okay. There is a non-planar operand, which is usually just called operand. Some people call it symmetric operand, where the definition is precisely the same, but instead of sequence of arguments, you have just a set of arguments.
So here curly brackets denotes sequence.
Yes, here this is a sequence of arguments. You see.
And one more question, could we take one x several times in one sequence?
Yes, of course. Good question. Very good question. For many years, I thought that operands have only one object. Well, of course, I am among those less famous people who knew that there exists a notion of operand, but didn't know the definition. So also invented it. So operand has one object. What does this mean? It means that for any n, you have a set of n array morphisms. All objects are the same, as you said. Even all xi are the same, and y is the same because you have only one object. So this operand is sometimes called monochrome, because in operand theory, objects are called usually colors. Monochrome. So for each n, you assign a set O of n. It's just this guy. And then you have operations. If you have n array operation and many operations of different arities, you can glue them together and get an operation of arity sum mi. This is an operand. Well, this is a planar operand. If these are sets and not if these are sets and not sequences, then at the end you have a symmetric group acting on this ON. So this is why this operand without adjectives is was sometimes called symmetric operand. Okay. I didn't say precisely what are the axioms of composition here, because if we are talking about sets, then you have well, I can't immediately say why should symmetric. Well, the definition is a little bit more involved, so that the symmetric group action appears automatically. I can't immediately say. Say how. So I can, but I don't want to spend time on this. Okay. Still, we don't have very much time. I want to present the idea, and okay. Now, what is connection between this notion of planar operand and monoidal category? Let me tell you. let us take a very convenient example to show the idea. Category of vector spaces is a monoidal category. It's even symmetric monoidal category, but forget about this. And how do we define tensor product of two vector spaces? We usually define it by a universal product. Okay. So it means that tensor product is not uniquely defined in sense of set theory. It's unique up to, okay. What is uniquely defined is the set of maps from X times Y to Z. Because this is bilinear maps from X, Y to Z. Okay? And then the object X times Y appears as something representing the corresponding function. It's a universal bilinear map, as people say. Okay? So you can use this idea that actually a structure on vector spaces underlying or more basic than the structure of monoidal category is the structure of operand, actually of symmetric monoid, of is actually not planar operand, but even of this operand when we define home set on collections just as the collection of bilinear maps. So the structure of operand on vector spaces is more obvious, more natural, more canonical than the structure of symmetric monoidal structure. Because according to our previous definition, monoidal structure is a bifunctor satisfying some properties. To make tensor product bifunctor, we should make some choices. We know that nothing depends on these choices, but still it's less canonical somehow. This is canonical in set theory. It's the set of maps that are linear in each of the arguments. Okay? So now we have the idea. We will say that a monoidal category is a planar operand satisfying some property, some universality properties. Let us help this. Still, in order to formulate universality, we need to have some category. Let C be a planar operand. C1 is the category that we already discussed. We take the same objects and only unary operations. Okay? So this is part of our structure. Now, given sequence we define a functor. From C1 to sets that carries Y to Why is it a functor? Because you can compose. If you have certain multi-operation, and if you have a map from y to y prime, which is also a multi-operation, but a very simple one, you can compose them and you get a multi-operation with values in y prime. So this is a functor. So given a functor, you can ask whether it is represented, okay, or co-represented, yeah, because it's covariant functor, it's co-represented. So this is condition one of monoidal category. So I want to define a monoidal category as a planar operator satisfying two conditions. The first condition, we can say any such functor is representable, or maybe co-representable. I don't remember the terminology. So the representing object is denoted by tensor product of x I. Okay, makes sense. Why isn't this enough? By the way, you can take empty set of objects. Empty set is also a finite set. This is a functor, and it's also representable. And the representing object is called one. Okay? Very well. Why isn't this enough? I can tell you why it's not this. By the way, this notion also makes sense. Unfortunately, I can't give you any easy example. This is what is called lax monoidal category. Lax monoidal category. What can be wrong with this definition? Why should we need an extra one? Let me tell you. This. So we have, for instance, three objects. I have the following map. No. Let me draw the picture. Like this. So I have here x1, x2, x3, x4. Okay. Here I can take x1, x2 times x3. It means that I take the universal object. Okay. Here I get x1 tensor, x2 times x3, x4, right? This is one universal thing. This is another universal thing. Now I have a map from x1, x2, x3, x4 to this guy. By universality, it gives me a map. Tensor product of all four of them to x1 times x2, x3, x4. You understand? I use only universal maps, but here is the total universal map, and here I use universal map in each one of the compositions. So I have a canonical map. This is an arrow in C1, right? This is an object and this is an object. But who can assure me that this is an isomorphism? Nobody. So my axiom mon1 does not give me that this is an isomorphism. So I can construct the map by universality, but I cannot claim that it's an isomorphism. So I add this as a second axiom. Any map from tensor product 1 and xi to, well, it's difficult to write down. It depends on the same objects, but I should, first of all, tensor product from K to L, but then tensor product the rest of them. Okay, so this should be an isomorphism. Once more, it's not a datum, it's a property, yeah? This should be an isomorphism. So this map is defined by universality, by the first property. But second property is that this is an isomorphism. So definition. A monoidal category is a planar opera satisfying mon1, mon2. We don't have associative constraints. We don't have many choices that are not unique somehow and arbitrarily chosen. Yeah, it's always better to have structure that it's unique. In this way, we can say what is a monoidal functor. Let us tell. First of all, what is a map of planar operands? Well, here there is nothing to tell. I think I can give you one moment to think about and you will understand. It's like a functor between categories. It's something with no choices, no isomorphisms unique. So a map of planar operands is just a map of objects, and for each collection of objects, the corresponding map of multimorphisms. Okay, it's absolutely clear thing. Now, is any map of operates of a planar operates a monoidal functor? No. It can be less one. Let me tell you. Given, okay, let C, D be monoidal categories. That is planar operates satisfying conditions non-1, non-2. Okay. A map of planar operates okay is a collection of okay for each x x1 xn y you have home C of xi y to home D of fxi fy, all right? And we know that these guys are representable by our axioms. So this is home over C1 of tensor x I y. And this is home over D1 of tensor f of x I f y. Let me concentrate. So how do I know that I have such a it's difficult to concentrate. I'm sorry. Let me write down what I should get from this. I should get from this a natural map from tensor product of f of xi to f of tensor product xi. So it's easier than I thought. We just take instead of y the same tensor product. Okay, We have here identity map. And we get a map from tensor product f of xi to f of tensor product xi. Okay? So this you always get. But nobody can persuade you that you will always get an isomorphism. So this is an extra problem. I will say mon 3. F is a monoidal functor if the canonical map like this is bijective. No bijective, it's isomorphism. These are objects, not bonds. I can give you a very elementary example of a functor that is lax monoidal, but not monoidal. The way it's a typical example of lax monoidal functor. Let me remind, lax monoidal functor is just a map of planar operands without the last condition.
Is meaningful when we write what CDB monoidal categories with planar operators satisfying on 1, 1, 2. In fact,
Sorry, I don't feel well. What's yes.
Is it true that when we write what CDB monoidal configuration, in fact, we don't think they are monoidal. We think it's just some configuration which planar operands satisfying mod 1 and mod 2 and mod 2. And after that, when we know they satisfy mod 1 and mod 2, we say that they are monoidal.
Okay, yeah, what I meant is the following. I said before that the notion of monoidal category is equivalent to the notion of planar operand satisfying these two properties.
Yeah, so
So when I say this, I just mean let C and D be two planar operands satisfying mon 1, mon 2. Yes. Then we have a map of planar operands, and then we can ask, do we need to require anything to say that this is a monoidal functor? Monoidal functor takes tensor product to tensor product at least up to isomorphisms. In our presentation, tensor product is defined by functor it presents. So up to isomorphism just is nothing. Okay. So and the question is, we have this map and this map, and we require it to be isomorphism. That's the property. If there is no this property, if C and D are monoidal categories and F is just a map of planar operands, people say that this is lax monoidal functor. So I want to give a simple example. C is the category of vector spaces. D is the category of sets. And the functor is the forgetful functor. So we take a vector space and we forget that it's a vector space. We just see that it has elements, so it's a set. So let us take two objects. So you can ask whether we have to verify this isomorphism for any collection or just for two. It's enough for two, but somehow, because multiple tensor product is isomorphic according to Mon2 to multiple tensor product of two guys. Because any tree like this, you can present as a composition of binary trees. So this functor, what does this mean? It means that you have a f of v times f of w to f of v times v. Yeah, this is a canonical map. So f of v is just v that we don't remember that it's a vector space. So it's a map from Cartesian product to tensor product. And of course, this will be precisely the universal bilinear map that appears in the definition of tensor product. Okay, so that's very, very meaningful situation. Now, what is the problem with this definition? I like it very much, but sometimes I remember that there is a problem with it. So today in the morning, I recall that there is a problem. The problem is that if you have a category C, and if you have a bifunctor, the tensor product, and if you have unit object and associativity constraints and all these axioms, and you replace C by C opposite, you obviously get the same type of structure because you only use isomorphism. Your associativity constraints are isomorphism. So once you change the direction, you can take inverse and it will work. Okay. In my approach, it doesn't work. Why? Because the very notion of planar operot is not self-dual because you have many inputs and one output. If you take the opposite object, it would have one input and many outputs. It's non-symmetric. You cannot just take opposites. So I don't know how to. I think there is no easy way to correct this problem. So just there is a obvious drawback in this approach, but otherwise it's very nice. I want to. Yeah, there is something that I skipped. There is a subtle point in the definition of operot. Well, as planar operots describe monoidal categories, just operots describe symmetric monoidal categories. But to see this, I should have been more careful in definition of operot. I said the only difference is that we have to replace sequence of arguments with set of arguments. But if you are still ready to hear the details, I will give details to make things straight. If you're tired, there is no meaning because I know what is to listen to 3-hour lectures and to try to understand some new ideas at the very end. So I'm ready to stop and I'm ready to continue describing the composition in non-planar opera.
I'm ready to continue.
Continue. Okay. In the worst case, you will just spend time without understanding. It's okay. So, opera. I will write symmetric in like that. So there is a collection of objects, and for a what is a set of objects? Finite set of objects. I don't know how to think about it, so I prefer to say that this is a map.
If we have two objects which are isomorphic, is it possible to take them both in one set?
Of course, even if they are equal. So sorry that I
No,
use
if they equal, so we don't think that set is like a structure in.
exactly.
Okay.
Yes. Exactly. What is a set of objects? It's difficult to say. I prefer to think about this as follows. You have a finite set X, and you have a map from X to the collection of objects of C. And that is for me a set of objects numbered by X. Okay?
So we can take one element several times.
Yes, we can. Of course. So this is a win. This is, by definition, it's collection. It's a finite collection of objects. Okay, now we want to talk about compositions. What is a composition? We have to take many finite collections numbered by one finite collection. I prefer to think about this as follows. We have Y, finite set, in the map P to X. These are finite sets, okay? It means that to any X in X, we assign y minus 1 of X. I will denote it Yx. And Y will be the disjoint union of Yx. So this is the way I will glue collections. So now, if I have an element alpha in form of here I have an object Z. Z is A is a collection of objects. Okay. And now I have B, a collection of B, a collection of objects numbered by Y.
Excuse me. What is actually the difference between what you call set and the sequence? If they are numbered by.
Sequence has an order, and this one doesn't have an order.
But it does have an order, no, because every element of X is some image. No.
Look, as a special case, did you understand that this for me describes the way of composition? It's not obvious, but because a map from Y to X is the same as presentation of Y into disjoint union of parts that are numbered by X. Some of them may be empty. It's like, equivalence relation. Any map of sets defines an equivalence relation of Y. This is very close to what I'm saying. But I allow some of the fibers to be empty. Okay? So this will describe me the diagram that appeared here. Here we also could have done the same if our finite sets would be totally ordered. And the maps were totally ordered.
It looks like a difference between two integrals, Riemann and Lebesgue. Exactly.
Really?
This is
Okay, maybe. But this is very far in my memory. Lebesgue integral. Okay, so what I want to say that here, since these X and Y are not totally ordered, you have as an example, just by Jack, you can take Y equals X and take any permutation. And the permutation still gives you an isomorphism between x1 times xn. And permutation gives you isomorphism between the action of symmetric group on home of A to Y to Z, right? You have here a collection of elements, and because there are bijections here, they act on this set. So, for instance, for an operand with one object, you remember I said operand with one object is a collection of sets numbered by natural numbers and certain operations. But this was for planar operand. This O of n is actually home, or was home of the collection of the same object n times. This is the only object we have, right? But in the non-planar case, we have the action of symmetric group on these guys. So the difference between planar operand and non-planar operand is that you have an action of symmetric group on this object. this what leads to the action of symmetric group on tensor power of one object on x to the power of n. Well, I think that's enough. There is, of course, notion of braided. Don't ask.
So in fact, any form in this case is just factor of form in operand, linear operand factor action of symmetry group.
Yeah, but you see, if you write down this sequence of elements, well, it's not that on all these objects acts the symmetric group. It acts the part of symmetric group which, well, if you have the same element many times, it's
Okay.
Sorry, but the symmetric groups, the group actually acts on the composition ones.
yes. But somehow objects are not very important, you know. In interest, well, for some time people studied operands. Well, the first definition was very general, but who reads definitions? So for a long time, or for instance, in applications in algebra, operands were just operands with one object because one color, people would say, because they described algebraic structures. Certain so there are algebras over operands, and operands somehow can describe what type of algebraic structure you want to work.
Is it a monoid? When you have one color, is it just a monoid?
No, it's not. It's not a monoid, but you can arrange a monoid from it. You mean is it a monoid in the sense that n the functor on?
Yeah.
It's a monad. It's the same, right?
I'm not sure.
Well, monoid for me is just a set with an operation, with an associative operation, and for you it's n the functor with this associative operation, right? Yeah. I call it monad. And well, operand defines a monad, yes, but monad is something more general.
But all tensor products in one color monoids is
No, you know, one color operand, I think is never a monoidal category or something.
yeah, okay.
Monoidal category has many objects, many colors.
Will you give an example of one color? Because I don't really understand. If we have one color, it means
One color operand. Okay. So you want me to give an independent definition of one color operand, but that is not planar but symmetric?
Yep.
Okay. It was called symmetric precisely when people thought only about one color operand. A collection of, well, once more, operands. I was talking about operands with values in sets. But sometimes you are more interested in operands with values in vector spaces. It means that this home set, you know, as there are categories and there are linear categories for which home sets are actually vector spaces and compositions are bilinear, right? A collection of objects since it's symmetric, action of Sn on O of n. For some reason, I remember that people wrote a right action. I don't know. Action. You can translate any action from right to left. I don't know what's more convenient. Compositions. Okay, now unit in O of 1. Okay. Compositions. O of n times O of n1. This is tensor product if these are vector spaces, and direct product if this is sets. These are compositions. And you require certain, well, it's associative. Slightly associative. It's long right, but you can imagine what it means. If each one of the is exactly as I wrote, you have here n. You can make from a tree a tree of height 1 always. Yeah. So associative. Some obvious unit condition. And compatibility of the actions of symmetric group. You have a map which is not a homomorphism. And this composition is equivalent with respect to this map. So what is this map? Okay, each one of these may changes the arguments. How to tell this?
Should it be kind of semi-direct form? Where Sn
Yes, exactly. Semi-direct product. So it should be like this.
I think no, because we get quotient by the right side.
Okay, yeah, you
So vice
put,
versa.
I can't think straight now. So tell how it should be.
Just no, the opposite direction.
Je-
Because we can forget about
I never remember what should be
Left X.
what acts on what.
Left and right. Symmetry group X on product, I think.
Mm. Well, it's I wouldn't tell that it's
No, the simple, like
It's
usually it's written in the opposite way, and then it's the left group rejects and the right normal.
okay.
So
I
if
don't know.
Then I guess
It's too
the
late
product-
now. I can't think straight. One should think what is the meaning of this.
The meaning is the left thing X on the right thing, correct?
But SN doesn't act here.
No, it should be the opposite.
Why?
and interchange multiplier directly.
Yeah, but then you should interchange them. Somehow it's well, I'm not sure I understand what I'm saying now, but mm. Well,
Yeah, sure.
if you see the drawings, you can make at most one sense of it, and there exists a meaning of this. I don't think this is a homomorphism of groups or something.
Should it go to a symmetric group of sum of mi's?
Some of MIs. No,
Yeah.
that's definitely true. That's definitely true. Look, you have this picture. Okay? Symmetric group of sum of MIs is group of permutations of these four elements. Now, given a collection of these guys, you have to define a permutation of this element. You do the following. You have an element here, you permute these branches. Now you permute these branches and these branches. This is here. That's how to get a result. To what extent is this a homomorphism or something? I don't want to think about this. So this is very combinatorial and I think very clear picture if you have these three in mind. And this is precisely what this condition wants to say. Now, so if you're talking about operands in sets, maybe it's not well. It can be interesting to talk about algebras over these games. But if you are talking about operands in vector spaces, all kinds of algebras you have in mind can be presented as algebras over this operand. What it means? It means that O of n will describe all n array operation on this object. And this composition says how you compose this operation. So Lie algebras, for instance, there is an operand with values in vector spaces that describes operations in all Lie algebras. Okay. Lie of 2 is one-dimensional vector space because there is only one binary operation. But the symmetric group of two elements acts on it by sign.
What do you mean by include?
Okay. I am sorry. There is an operand that describes operations in Lie algebra. Maybe, well, if you want 10 more minutes, I will describe two operands. The first, which is more easy to understand, commutative algebra. The second is also, well, three. The second is also easy to understand, associative algebra. And the third, which is much more difficult to understand.
It's about root system operator which related to the root system.
No root systems, no. Just remember what are the operations in each type of algebra. So, for examples, we are now talking about operands with one color. One color operands with values in vector spaces. It means that all our home sets are vector spaces. First, I denoted it like this, home. As usual, it's a collection of home of n for different n's with the action of symmetric group. Get home. Com means commutative. It describes operations. Com of n describes n array. This is vector space of n array operations on a commutative algebra. Actually, there is only one operation. Just take n elements and multiply them. Order is not important. Okay? So this is just one-dimensional vector space. C. Okay? And the symmetric group, how does it act? Order is not important, so it acts trivial. All multiplications, okay, takes the only generator and multiply, you get one. Okay? So that's the operand for governing commutative algebras. I won't say in which sense, but I think you feel something because it describes all operations.
So
And
how to produce?
Pardon?
How to produce a commutative algebra separate?
No, you cannot produce a commutative algebra for this operand. But if you take
Not for, but for.
no, you cannot produce. But commutative algebras are algebras over this concrete operand. There is a notion of algebra over an operand. And this is algebra over these operands are commutative algebras. At the end, I am ready even to give a definition. What is algebra over an operand? You can imagine. Associative, that's a little bit more interesting. It will describe all n-array operations on an associative algebra. As of n is, what are n-array operations on an associative algebra? You just order these n elements and multiply them. We discussed that associativity condition means that if you have an ordered list, you can multiply them. Okay, how many different operations do you have? Okay, n factorial. Well, this is just, you have different orderings, give different operations in associative algebra. So this, as a representation of symmetric group, is just, how you call it? Regular, I forgot.
So we define it.
Regular representation, yes?
No, it's not direct.
Pardon?
Oh.
Yes. Of dimension n factorial. All possible permutations. So that's it. Well, you have to be careful to define the composition, but it's not difficult. So this is very difficult, very easy things. Commutative algebras are governed by this operand. Associative algebras are governed by this operand. Lie algebras. This is more sophisticated. Let me say what is Lie2. These are binary operations in Lie algebra.
I'm sorry. What if we want to obtain a commutative but not associative code?
Well, it will be something. Yeah, you can do it, but it will be something that I don't know how. Well, I have got accustomed to call commutative those that are associative and commutative. If you want to describe commutative things, you can do it. It will be certain operand, but I don't have name for it. And I cannot immediately say what it is. It's quite huge. Because commutative non-associative multiplication, well, I don't know. Yeah, this is an exercise in representations of symmetric groups, I think, to describe all n-array operations on this. But this is not very trivial thing. This is even not very trivial thing, even though it's not difficult. Let us think of Lie of 2. That's interesting. Lie of 2, there is only one operation, one binary operation in Lie algebras, up to constant. It's just break, okay? But if you transpose the arguments, it will change the sign, right? So it means that this is non-trivial representation of symmetric group S2. It's sign representation. about Lie of 3, I think let us calculate the dimension. I don't want to describe more than that. How many expressions we have from 3 elements? This is double commutator, right? We have, pardon? Yeah, dimension is 2. Why? Well, because symmetlicity, Jacobi identity, exactly. So the dimension is 2. Well, there is a formula for Lie of n as representation of symmetric group, but I don't precisely remember what's. It's some induced representation for from Sn minus. I don't remember. From cyclic group to of an element to Sn, something like that. And of course, there are compositions. It's a non-trivial thing. How to describe it? You take 3 to describe Lie of n. You take 3 Lie algebra with n generators. It's multigraded by n degrees of each of them. And you take the part which is linear in each argument. 1, 1, 1, 1, 1. Has multi-degree 1, 1, 1, 1, 1. Well, it's a general answer. It's more or less easy, but you know, this is a part of the theory that goes in absolutely not the direction of the lecture, but orthogonal, right? We were interested in description of multiplicative structures of symmetric monoidal categories, for instance. We came to the language of operads, and operads that are very far from being symmetric monoidal categories are just these operads with one object. They describe some sort of algebraic theorems, like associative, commutative, linear, and so on. Okay, that's more than enough for today. Yeah. Thank you.